We'll start with number 2. Which of the following is true for a system whose equilibrium constant is relatively small? Remember what the constant represents. If we have an equation that's generalized, then the equilibrium constant is products, concentrations. Oops, should be a C. And reactant concentrations in the denominator. Now, I don't know what possessed Waig and Associates to write it that way, putting these on top and didn't put these on top instead. They may have had good reason, or maybe they just figured, flip of the coin. But once it's established, then we can say something about the equilibrium and the size of this value. If this is relatively small, that means this is a very small value compared to that value, which means most of at equilibrium, you're still mostly reactants. Okay, so the equilibrium lies to the left when we talk about the constant in those terms. Number 3. Let's see if I can get away with leaving that up there. I'll talk about 3 now. For the equilibrium system, inflation leader, there was a I'm going to need all my space. Okay. So let's just erase this and start from scratch. So for this reaction, CO2 and hydrogen is in equilibrium with carbon monoxide. Yep. And water. And that's gas. And the enthalpy for this reaction is 42 kilojoules. They're saying per mole. I heard the expression per mole of reaction. In other words, as written, that's what you get out of it. Since these are all coefficients of 1, then you can say per mole of any one of them. K equals 1.6. 1.6, which is CO, H2O, and CO2. These are all to the first power. That's what that means. If 0.15 mole of each is placed in a 1 liter thermally insulated vessel, so 0.15 molar is the non-equilibrium situation. So 0.15 molar of each one. Okay. That was also at 1260 K. So temperature we're given is 1260 K, and that's the K value at this temperature. Okay, that's everything we know. As the system comes to equilibrium, what happens? Well, let's look at these values first. If we calculate Q, right? Q is just 0.15. Actually, it's not square brackets because we're not at equilibrium. I think you can see where this is going. That's equal to 1. So if the Q is less than the K, that means this is too small, correct? If Q is less than K, then the reaction is going to move to the right because this is too small. It makes this value smaller than it should be. This needs to be bigger. So it's got to move to the right, okay, to reach equilibrium. Okay, when it does that, what's going to happen? Well, if it moves to that side, we know for this is an endothermic reaction, right? Plus value. That means delta H is on this side. So the temperature should decrease. We're going to move to the right, temperature should decrease. So that means A or B, temperature decrease. The mass of CO2 would increase or decrease. CO2 would decrease. So that's why B is the answer. And we had to put all that stuff up there to understand where the reaction started and then where it ends up in order to answer that question. Right. So I wasn't just spinning my wheels doing that. All right. Let's see. We've got, given this equation, at a particular temperature, K is a value 4 through 6. We're going to answer these questions. All right. All right. 2A yields 2B plus C. 4 through 6. Well, actually, we're only doing 4 and 6. 2A plus B. No, yields. Yields 2B plus C. Correct? Yep. At a particular temperature, K is 1.6 times 10 to the 4. All right. Addition of chemical B to an equilibrium mixture will do what? If we add B, it's going to cause the reaction to shift to the left. All right. Which means A would increase, which was A. Yeah. A would increase. Okay. How about 6? Raising the pressure by lowering the volume. Okay, if we increase the pressure by decreasing the volume, what's going to happen? We've got 2 moles on this side, and we've got 3 moles on this side. So when you increase the pressure, the response is going to be to reduce some of that pressure by reducing the number of moles of gas, according to Avogadro's law. So the shift is going to be back to the left again, which would cause A to increase. Yep. Again, A would increase. Now, why did I skip 5? At a higher temperature, K equals, let's go ahead and do 5. Since we got this stuff already up here. At a higher temperature, so this is at T1, at T2, where T2 is greater than T1. The K now is equal to 10 to the minus 5. So by increasing the temperature, we've shifted the K toward the negative. So what does that mean? Well, if you increase the temperature, the equilibrium expression Let's just put it up here so we can talk about it intelligently. If you're making this smaller, then you're making the product side smaller. And we did that by increasing the temperature, which means that we probably have heat on that side. So you increase the temperature, you're going to drive it back this way and decrease these amounts to make that smaller. So this is an exothermic reaction. Placing the equilibrium mixture in an ice bath. Okay, so we know we've characterized the situation like this. We know where delta H is located because of this. Now, if we, at this higher temperature, if we place it in an ice bath, lowering the temperature, that is, we're removing this side, it's going to shift it back this way and make more B and more C and less A. Will cause B to increase. Yeah, cause B to increase. Maybe that's why I didn't put that one in there. Because it takes some mental gyrations to get there. But it was worth the effort, I think. See if we really know what we're talking about. All right, now we can move on about number 8. Or maybe I didn't do that one because this one's going to be similar. It's possible. Rather than write that on the board, let's try to work from this equation on the page. This complex ion, cobalt with 6 waters, plus 4 chlorines, the chloride ions. The chlorides replace the waters. And we also get an indicator of color change. It goes from pink to blue. When cobalt 2 chloride is added to pure water, we hydrate the cobalt. The hydrated form then reacts with chloride ions to set up the equilibrium shown here. Okay, which statement below describes the change that the system will undergo if hydrochloric acid is added? If we add hydrochloric acid, then we're going to shift toward the blue side to become more blue. So A is correct. B can't be, because you can't have both of them. Can't move both directions. And the equilibrium will shift to the right. So A and C are both true, 2 of these. All right. Consider this one. Number 9. Let's see. Yeah, I can write this one up here. 2H2 gas and X2 gas. Is in equilibrium with 2H2X. X as plus energy. Okay. Addition of X2 to a system described by the above equilibrium. We add X2. That's going to shift to these products. H2 will decrease. Yes. X2. Oh, okay. I know how I put this one in here. This one will definitely decrease. Now, this one will decrease from the added value, but all of the added amount that we added to it will not be consumed. Because once it reaches equilibrium, we've used up some of it, but not all of it that we added. So based upon the original amount of X2, we actually have more X2 than we started with. We're at a new equilibrium position, right? Remember, we added this to make this reaction move to the right. So we didn't add any of this. We consumed some of it. So that made it go down. But we did add some of this, and only some of that was used. So what was there already, plus what we had left over, some of it was used, but not all of it. So the end result is the position says, now this is a little bit higher. It's not as high as it was when we added it, but it's still higher than it was when we began before we added. See what I'm getting at? It's a different position. Yeah. I think that's why I put that one in there. H2X will increase, not decrease. It'll definitely have an effect. Cannot possibly be carried out. I was searching around for something to put in for E. Okay, 11. Yeah, that's a common error. When we say it shifts, don't let your mind be hamstrung by the original amounts because you've added some. Right? So you're going to use some of that up, but not all of it. You're just going to use enough to reach equilibrium again. Number 11. Which of the following statements is true? When two opposing processes are proceeding at identical rates, the system's at equilibrium. That's a good answer to me. Right? If we look at the others, they should be all false. Catalysts are an effective means of changing the position of an equilibrium. No. Catalysts have nothing to do with equilibrium. Catalysts are kinetics. They speed up the reaction in both directions, which is characteristic of inorganic catalysts. Inorganic catalysts are indiscriminate. They speed up the reaction in both directions. So you can get to equilibrium quicker, but you don't change the equilibrium at all. Concentration of the products equals that of the reactants and is constant at equilibrium. Sorry, no, it doesn't work that way. We spent enough time on that one. Let's move on. 14. Not that. Consider the reaction represented by this equation. 2SO2 and O2. 2SO2 plus O2 is in equilibrium with 2SO3. And these are all gases. Okay. This system's at equilibrium. Which of the following explains what happens after the addition of oxygen gas and assume constant temperature? We're going to add oxygen gas to an equilibrium situation. So we know that it's going to move left to right. Doesn't say anything about the energy, right? Okay. So is the K going to change? No. The equilibrium constant stays the same as long as the temperature didn't change. So it's either D or E. The amount of SO3 gas increases. Right. So that's E. How about, let's see. We're focusing on this one, 15. Consider the endothermic reaction. 2BrCl yields Br2 and Cl2. What will be the effect of the equilibrium of, okay, we've got two things going on. If we change the volume at constant temperature, is anything going to happen? Look at the number of moles. No, same number of moles on both sides. Equilibrium will not shift if you change the volume. So changing the volume, we're looking at no change in equilibrium for the A part. So that's either D or E, right? See, I didn't put that number here. So the first part is no change because it's equal number of moles on both sides. Second part, increasing the temperature at constant volume. If we increase the temperature, endothermic reaction. Okay, there's the key. It's endothermic. That is, delta H is on this side, right? So if it's on this side and we increase the temperature, it's going to shift to products. So that's why D is the answer. So B is shift products. All right. Skip a few. Lots of repetition in here. How about number 20? The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. Okay, we've been working with gases up to this point and nothing else. But now we're looking at a reaction that has a solid as a reactant, and it's yielding a liquid plus a gas, right? Oh, and delta H is 43.4. Delta H, 43.4 kilocalories per mole. Okay, following reaction. HGO, mercury 2 oxide in the bulb could be increased by what? Well, let's see. The only way we can change this equilibrium, because solids and liquids don't have an effect on the equilibrium. The only way we can increase HGO is add more oxygen. If we add, this will have no effect. We add more mercury, it won't have any effect. If we remove some of this, it won't have any effect because the equilibrium expression is simply that. That's it. So, oh, I missed that one. Since there's 1 mole of gas on this side and no moles of gas on this side, if we decrease the volume, we're going to force the reaction in this direction. Difference between 1 and 0. Yeah, that'll do it. All right, 21. At 500 K, 1 mole of gaseous ONCl is placed in a 1-liter container. And this is the reaction that is in equilibrium. 2 ONCl. It's gas, right? Well, they're all gases. 2 NO and chlorine, right? Okay, this takes place at 500 K. Let's see, got a 0. At equilibrium, 5.3% dissociated according to this equation. So 5.3% dissociated. All right. How are we going to deal with this one? Time for the ice table, isn't it? Okay. Let's see, that's in the way. Let's move this over here. 5.3% dissociated. And the question is, what's the equilibrium constant? Okay, so KEQ is going to be NO squared Cl2 to the first power over ONCl squared. All right. what does 5.3% dissociated mean? We put 1 mole in 1 liter. So we start off initially with 1 molar, right? 1 molar, and nothing over here. That's our beginning condition. And at equilibrium, we're 5.3 dissociated. So 5.3% of that is gone now. So minus what would be 5.3% of that? It'd be, if that's 100, then it'd be 5 here, right? Correct? 5.3 dissociated. Okay. That means that this one is also going to be an addition of 0.053. And this one's going to be half of that amount, which would be 0.027 rounded off. Okay. So yeah, we can calculate. This is going to be at equilibrium, that value, 0.053, that value, and then what's left over? 7.4. Oops. 9. Does that add up to 1? Yeah. Okay. So let's plug our numbers in and see what we get. Let's see. We're going to have 0.947 squared. Let's see. No, we're not. Wrong one. Try that again. 0.053 squared, and then 0.027. And then on the bottom, we have 0.947 squared. There we go. Okay, I get, let's see, that's only 2 significant figures. 8.5 times 10 to the minus 5. Close enough. 8.3 times 10 to the minus 5 is the closest number. Rounding error of some kind. Yeah. Or we could look at the way I worked it out before and see if I ended up with the same problem. Okay, 24. Well, I check my messages. What's happened to Augusta? Oh. Messages there. Check my email. Um, no, not communicating. Next one, 24. Nitrogen gas reacts with hydrogen gas to form ammonia. Good old Haber. At 200 degrees in a closed container, 1 atmosphere of nitrogen gas is mixed with 2 atmospheres of hydrogen gas. At equilibrium, the total pressure is 2.2 atmospheres. What's the partial pressure of hydrogen gas at equilibrium? Okay, so we got to write and balance the equation before we can set up our ice table. So let's see, it says nitrogen plus hydrogen. Nitrogen plus hydrogen yields ammonia. Okay, so we need 2 of these and 3 of these, right? That should balance the equation. What else are we told? Temperature is 200 degrees. 200 degrees C. In a closed container, 1 atmosphere of nitrogen gas mixed with 2 atmospheres of hydrogen gas. Okay, we're going to be working with partial pressures here. One atmosphere of nitrogen and 2 hydrogen. And that's 0. At equilibrium, the total pressure is 2.2 atmospheres. So at equilibrium, this plus this plus this equals 2.2 atmospheres. Okay. All right. So if we're going to calculate the partial pressure of hydrogen gas, I suggest we make this change equal to, well, actually, 6 and 1/2 does the other. The change we could call X. So if we say we lose X here and we lose 3X here, then we gain 2X there, right? I mean, you could pick a different ratio of X's in there if you wanted. But this way, if I make that X, then I don't have to deal with fractions. Okay, so this is going to be 1 minus X. This is going to be 2 minus 3X. And this is going to be 2X. And that's all equal to 2.2 atmospheres. Right? So, let's see. Let's combine all of our X's, right? They're all add or subtract. So 2X minus, that's minus 4X, and a plus 2X is a minus 2X, right? That takes care of that one, and that one. And then this is going to be 3. That's equal to 2.2. So minus 2X equals a minus 0.8, right? If I take this 3 to, it's a negative on that side, then it gives me a negative 0.8. And X equals 0.8 divided by 2, because the negatives cancel. 0.4 atmospheres. That's X. But this is 2 minus 3X is the final pressure of hydrogen. So 2 minus 3 times 0.4 equals what? 0.8? Did I do that right? I tried to do it in my head. This is 1.2. Wait a minute, that's not right. Let's see, what did I do wrong? X is 0.4. 3 times 4, 401. It's 3X. Ooh, that's not going to work, is it? Got the right answer, but how did I end up like that? Oh, yeah. Okay, yeah. 3 times 0.4 is 1.2, isn't it? Minus 1.2. 2 minus 1.2. No. Yeah. 0.8. I did it right. I just didn't trust myself. It's a calculating in your head is a perishable skill. You have to keep working at it. Do it every now and then just to keep your brain cells synapses go in the right direction. So that was fairly simple to solve. We didn't have to go through a quadratic solution because of the way the problem was set up. 25. Wait a minute. Same equation. Okay, it's just a different approach. All right, well, we can do that again. Gives us the balanced equation. Let's see, 3 hydrogens plus nitrogens yields 2 ammonias. And what else are we told? 2 moles of nitrogen, 4 moles of hydrogen added to a 1 liter container. That means we're starting off with 2 molar nitrogen and 4 molar hydrogen. And that's 0. So those are our initial conditions. All right, what else are we told? Equilibrium concentration of ammonia is 0.55 at 700 degrees. 700 degrees C. And the ammonia concentration at equilibrium is, I had there a minute, 0.55. 5 molar. So how did it get there? Well, if it started at 0, we had to add it right here, right? Okay. So if that represents 2, then half of that would be here. 5 maybe. No, that's not right. 2. Seven, 5, 7, 5. There we go. This is subtracted from that. And this is 3 times that is subtracted. So that would be 22. 2 and 6 is 8, right? 3 times this value. 2.
Yeah.
Should say, okay. All right, so now we can subtract that from this one. It's 1.7 minus 2, and 2 from 9 is 7. Yep. And this one would be 5. 2 from 9 is 7, and 8 from 9 is 1. This is 3. Yep. Okay, so those are our values. And the question is the value of K. Okay. So K is going to be NH3 squared over H2 to the third, and then N2. So ammonia is going to be 0.55 squared, and then hydrogen is, as is, 3.175, to the third power, excuse me. And then nitrogen is as is, 1.725. There we go. So let's see what we get. Squared and 3.175. Enter. Okay, I get, let's see, 2 significant figures. -3. Yeah. Did you get that too?
Yeah.
Okay. All right. 26. Okay. Given the equilibrium constants for the following reactions, what's the K for the system? Okay. Hess's law. Except we're using it for equilibrium. Okay, our target equation is 2Cu, right? Plus O2 is an equilibrium with 2Cu. Okay. So we're after this expression. What's that equal to? Based upon these other two equations. So we have the first one, the K1 equation, has oxygen and copper on the correct side, but we need half of it. Right? We only need 2 coppers. No, the oxygen's right. It's just that maybe we ought to leave it alone. Think so? No, we better take a half. Better take a half of it. So 4Cu plus O2 is in equilibrium with 2Cu2O. And that's K1. So if we take a half of that, right? What is that going to do to the K1? To the half power, right? Anytime you multiply something times an equation, it becomes the power of your K. So this is going to be to the 1/2 power. And now we have 2 here, 1/2 there, and 1 there. Okay. So we've taken care of the copper. Now we need to look at oxygen and CuO. The second one has CuO on the wrong side. So let's put CuO on this side. Right? 2CuO on this side. And then flip to the other side, Cu2O, Cu2O solid, and then 1/2 O2, like that. Okay, so we flipped it. So what does that do to this one? When you invert an equation, you invert the constant because it puts the reactants where the products were and the products where the reactants were. So this becomes that. Okay. Now, if we add them together, what does that do? Well, you got one of these here and one of these there. That's gone. This checks out here, here. These two together check out there. And this one is correct. So what do we do with these now to get that value? KEQ is equal to, you multiply them. Multiply the K's together. K to the 1/2 times 1 over. This is K1. There we go. So K to the 1/2 over K2. K to the 1/2 over K2E. Yep. All righty. See what we got here. 28. Do it. Exactly 1 mole of N2O4 is placed in empty 1 liter container. Means it's 1 molar. Allowed to reach equilibrium described by this equation. If at equilibrium the N2O4 is 37% dissociated, what's the value of the equilibrium constant for the equilibrium under these conditions? All right. So we've got our equation is N2O4, right? Yep. And it gives us two NO2s. Right? And we want to know what K is, which would be NO2 squared over N2O4. And our initial conditions, 1 molar, correct? I got enough zeros in there? Yep. 1 molar here, nothing there. Change equilibrium. We are told that at equilibrium, N2O4 is 37% dissociated, which means we lose 37% of that. Correct? Yep. So that means this is 0.63. And this would be plus 0.74, right? There we go. Did I lose anybody?
Where did the 7.4 come from?
The stoichiometric ratio.
Oh.
If we lose 1 here, we get 2 of them over here.
Okay.
Okay. All right. So we just plug in the numbers. Let's see, 0.74 squared over 0.63. I get 0.87. All right. Let's see, scroll, 29. Consider the reaction. H2I2 is 2HI. H2 plus I2 HI, 2HI. For which K is 44.8 times, K is 44.8. 44.8. At a high temperature. Okay, it has to say high. Why? Because at room temperature, iodine is solid. So we got to turn it into a gas. So this is a gas. That's the only way this makes sense. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 at equilibrium, determine the equilibrium concentration of hydrogen. Okay. CE. All right, we got the same amount of, this is an equimolar mixture of reactants. This is 0. But we've got the same, we're starting off with the same amount there, molarity. And what else? The concentration of the product is 0.5. 0.5. Oh, okay. So this got there by that, right? Molar. So how did it get there? Well, it's twice whatever was over here. Right? So whatever we lost over here is a half of what that is. So this would be minus 0.25, and this would be minus 0.25. Determine the equilibrium concentration of hydrogen. All right. I'm wondering if we need to, do we really need to determine what the original concentration was? If we're going to use the equilibrium value, we probably do. We do have to say x minus 0.25. X minus 0.25. Yeah, I don't see any way around that. So this is going to be 0.5 squared, right? And this is going to be x minus 0.25 times x minus 0.25. Right? So this is the same as saying 0.50 over x minus 0.25, all that squared, right? Because this would be x minus 0.25 squared. And as I recall, early mathematics tells me that if this is squared and that's squared, then the whole thing as a quotient can be squared. Right? So this is equal to 44.8. So if we take the square root of both sides, that leaves us with 50 over x minus 0.25 and the square root of 44.8. Follow?
I think
The trick here is to say this is x minus 0.25 squared. So if this is squared and that's squared, we can combine them. Okay. Then you just take the square root of both sides. That reduces this to this value and then the square root of 44.8, which is 6.6933. And then we just solve for x. Okay. 0.50 equals x minus 0.25 times 6.6933. And that would be 6.6933x minus a quarter of that value, which would be 1.6733 was this. And we get that one on this side. And that's plus 0.5, which is 2.1733 equals 6.6933x. And then x is simply this one divided by that one, which is 0.3247. That's x. It asks us for the concentration of hydrogen. So this would be x minus 0.25 equals that minus 0.25, which would be, let's see, standard notation. Which one am I on? I'm on the bottom one.
Yep.
Scientific notation. That's good. 7.5 times 10 to the minus 2 molar. Did I lose anybody?
you lost me.
Okay.
Is this the same thing you did here, or am I trying to look at both of those and it's confusing me? I think it's closer to the bottom.
Oh. Yeah.
Is that the same thing that you did and I'm just confused?
I got the same answer.
Okay.
I just went about it differently.
Okay.
Yeah, I did. I made it more complicated.
That's confusing.
Yeah, that's a quicker, easier way. Maybe if I had made made these equal to x.
Whenever right here,
Uh-huh.
I don't understand what you did to get from the 5/8 to the 7.
Well, 0.25 divided by 44.8 is 5.58 times 10 to the minus third.
Okay, and then what did you do?
And then I took the square root of both sides.
Okay,
Yeah.
that makes sense.
So, the moral of this story is there's more than one way to solve the problem.
Yeah.
Number 30. At least I'm consistent with scrawling my calculations across the board. So you have to go like this and like that to get the answer. Number 30. Let's see. 2HF yields H2 plus F2, K equals 1 times 10 to the minus 2. Given 1 mole of HF, 0.362 moles of H2, 0.75 moles of F2 are in a 5-liter flask. What's the reaction quotient? Oh, okay. So if we're working from this equation, and these are all gases, H2 is F2. It doesn't matter what K is. If we're going to calculate the Q, if we're going to compare the Q to K, then K does matter. But if we're only going to calculate the Q, we just need to know this, H2 in parentheses, F2 in parentheses, and then HF squared. Now we just need the concentration values. So if this many moles of each one is in a 5-liter flask, so HF is going to be 1 divided by 5 moles per liter. 1 divided by 5 is HF. Okay. H2 is 0.362 divided by 5. And F2 is 0.75 divided by 5. Okay. Now, let's see. I don't want to make this too complicated, but I'm trying to simplify it before I actually do calculations. This is 1 squared over 5 squared, right? This is 362 times 0.75 over 5 squared. So 5 squared is here and 5 squared is there. Correct? 5 squared is here, 5 squared is there. So we can get rid of the 5 squareds. And this is actually 0.362 times 0.750 over 1 squared. Let's see if that gives us the same answer as 0.362, 0.75. I get 0.272. Yep, that's the Q. Did I lose anybody?
No.
Yeah, that's squared, 5 squared. This is 5 squared. They cancel and leave us with 0.362, 0.75 over 1. That's how I got that. 31. Let's see, how we doing with time? Okay, I've used up an hour. Consider the following equilibrated system. 2NO2 yields 2NO plus O2. If the Kp value is 0.604, what's the equilibrium pressure of O2 gas if NO2 gas pressure is 0.52 atmospheres and P is 0.3 at equilibrium? Okay. Yes. And this yields 2NO gas plus O2 Yes. All right. And our KP is going to be equal to partial pressure of NO, pressure squared, times partial pressure of O2 divided by partial pressure of NO2 squared. Okay. And that's equal to 0.64. 602, excuse me. 602. Nope, 604. Try that again. There we go. That's given. At equilibrium, the O2 pressure is 0.52 atmospheres. And we're trying to figure out pressure of O2. Oh, yeah. NO2 gas pressure at equilibrium is 0.52. Squared. The NO pressure is 0.3 squared. And then there's O2. All right, we don't have to do an ice table. That's just a simple calculation. I'm going to square this one and then times that one. Right? 0.52 squared is 0.27 times, let's do that, 0.2704 times 0.604. And there'll probably be less confusion. 0.3 times itself is 0.090 PO2. Okay, squared this one. Then I squared that one over here, multiplied times this one. And then PO2 would be 0.2704, 0.604, and then divided by 0.09. So I get PO2 is 1.81 atmospheres. That's C. All right. 32. Unless your questions. Okay. Thirty-two. Carbon disulfide and chlorine react according to the following equation. Let's see, 2.14 moles of CS2 and 5.85 moles of Cl2 placed in a 2-liter container allowed to come to equilibrium. Mixture is found to contain. How many moles of Cl2 are present? Okay, this is going to need an ice table. So we have CS2, carbon disulfide, and chlorine gas is in equilibrium with S2Cl2 plus carbon tetrachloride. Okay. So and our equilibrium expression, we're in terms of molarity. Is a KEQ given? I don't see it. Okay, we may not need the KEQ. Let's put what we know up there. 2.14 moles of CS2 in 2 liters. 2.14 mole per 2 liters. Okay. And then chlorine is 5.85. 5.85 moles per liter. Moles per 2 liters. Okay. And 0.620 moles of Cl2, carbon tetrachloride. 0.620 moles. 0.620 moles, still in 2 liters. Okay. That's what we're given. And the question is, how many moles of Cl2 are present? Okay. Well, what's the stoichiometry? We start off with 0 here and 0 here. We end up with that there. That means this had to be 0.620 moles. Right there. So how did it get there? Well, it had to lose the same amount from this side. This was minus 0.620 moles per 2 liters. And that would make this one minus zero, multiply by 3. Moles in 2 liters. Oh, they're all in 2 liters. So just subtract that from that. If the question is how many moles are left over, everything's in the same size container. 5.85 minus 1.860 is 3.99 moles. Okay. So we didn't need to know what K was. It helps me to throw everything up on the board, and I can see relationships. I would have no luck doing that one in my head. All right, 33. Minus 80 degrees Celsius, K for the reaction N2O4 yields 2NO2 is 10 to the minus 8th. We introduce 0.047 moles of N2O4 into a 1 liter vessel. Let the equilibrium be established. Total pressure in the system at equilibrium will be. Okay. So talking about N2O4 gas is at equilibrium with 2NO2 gas. The K equals 4.66 times 10 to the minus 8 at minus 8 degrees. Minus 80 degrees C. Okay. So what are the initial conditions? 0.047 moles of N2O4. 0.047 moles introduced into a 1 liter flask. So that's molar. It's a 1 liter flask. Allowed to come to equilibrium. Okay. Start off with that much. And change here. Okay. So we know we're going to lose some of this because that's 0. So we're going to lose a little bit of that, and we're going to gain that much on that side. Okay. All right. 0.047 minus x, and this is 2x. And then, well, let's look at where we're headed. The total pressure in the system, right? We're not told. No. I'm thinking that if we want to know the total pressure, we're going to have to go back to this law. We got the temperature. R is a constant. Volume is 1 liter. And pressure is going to be our solution. So we need to find the number of moles of gas at equilibrium. Then we can calculate total pressure, right? Okay. So let's say K is going to be equal to squared, 2x squared, right? And then down here, we're going to have 0.047 minus x to the first power. That's equal to 4.66 times 10 to the minus 8. All right. So I think, is this the way I worked it in the problem so
I
far?
think so, yeah.
Okay. I just don't want to spin my wheels for half an hour. Okay. So this is one of those cases where we can use an approximation. Because K is so small, this value is going to be extremely small. But we can't get rid of it because we need that x. But we can say that this x is so small that this is going to be approximately equal to, let's see, 4x squared over 0.047. And we can drop the x. Okay, that's the approximation. And that's still equal to 4.66 times 10 to the minus 8. Okay. Now we can solve for x. We just need to multiply this times that. .047, and that's equal to 2.1902 times 10 to the minus 9 equals 4x squared. And then we divide this by 4, right? Which is 5.476 times 10 to the minus 10. I divided this by 4, and then take the square root. So x equals 2.34 times 10 to the minus 5 molar. Okay, so 2 times that is going to be this value. Right? 2 times 2.34 times 10 to the minus 5 molar is equal to 4.68 times 10 to the minus 5. And this is going to be 0.047 minus that x. So I'm going to, let's see, invert that, say 0.047. This is going to be equal to 4.698 times 10 to the minus 2. All right. We're essentially the same molarity because this is so small, right? It's so small. If we add this back to that one, we're going to, for our total moles, we're essentially going to be there. 0.047 molar, which is how many moles? 0.047 moles. So this is 0.047 moles. This is 0.08206. And this is 273 minus 80. And this is equal to 1, and this is P. So P is equal to that, 0.047, 0.08206, and 273 minus 80 times that. And I get P equals 0.74 atmospheres. Could have saved ourselves a whole lot of trouble if I just recognized that this thing is so small, it's not going to change. It's not going to change the total moles of gas. Total moles of gas is essentially 0.047 moles per liter. And then we could go straight to that equation. Right? If I were taking a test and I were a student again, I'd be thinking in those terms, right? To get the shortest distance between point A and point B gets me to the next question. All right, 34. A sample of solid ammonium nitrate was placed in an evacuated container and then heated so it decomposed explosively. Okay. N2O plus H2O. Total pressure at equilibrium is found to be 2.63 atmospheres at a temperature of 500 degrees. Calculate Kp. And then I added Kc in there because I figured it was a natural progression. All right, so we're working from ammonium nitrate, solid, and it produces N2O gas plus 2H2O, correct? Yeah. At equilibrium, the total pressure in the container was found to be 2.63 atmospheres. So the pressure of N2O plus pressure of H2O equals that value, 2.63 atmospheres. Okay. So far, that's what's given. And temperature is 500 degrees. C. All right. I'm gonna go ahead and change it. Probably gonna need it anyway. Let's see, 973K. All right. What's Kp? Well, Kp, we calculate Kp is equal to P of N2O to the first power and P of H2O squared. And ammonium nitrate doesn't matter because it's a solid. Okay. The total pressure is this. What we need is to figure out what each one of these is. Okay. If, let's see, the change, let's see, at equilibrium, we're going to have so much of this, and then we're going to have twice as much of that, correct? Yeah, that's their stoichiometry. So if this is X, then that's 2X. If this is X, then this is 2X is equal to 2.63, right? Yeah, because partial pressure is proportional to the moles of each of its components. We learned that from Dalton. Okay, so we can find out what X is. All right. X is 2.63 divided by 3. Right? Because that's 3x, then X would be 3 into that. 0.877. So this is going to be 0.877, and this is going to be 2 times that. 1.753 atmospheres. Well, actually, it's moles. No, it's atmospheres. It's atmospheres. Sorry. So if we plug this in here, is that what we're after? Yeah, we're after KP. So this is 0.877, and this is 1.753 squared. So I'm going to square that one because it's already in here. And then 0.877 times that. And I get 2.70. Okay, that's KP. All right, if we're going to go KC in molar units, we need to go to useful information. There's an equation for that. Remember where it is? It's, where is it? Here it is. KP equals KC RT delta N. Okay. So what's delta N? The change is final minus initial. Well, final is 3 and initial is 0. So this would be 3. R 0.08206. T is 973. And KP is 2.70. So we can solve for that one. Right? So let's multiply these two. 0.08206 times 973. And then take it to the third power. Okay. So this part, 2.70 equals KC times 5.09 times 10 to the 5th. So KC would be 2.7 divided by that value. 2.7 divided by 5.9 times 10 to the 5th. And I get 5.30 times 10 to the minus 6 is KC. Is that right? Did I calculate that one in the useful? Okay. That's just an exercise in using that formula. Right. Scroll. 36. Starting to get weak. Sat down for a while. Certain temperature K for the reaction 2NO2 to N2O4 is 7.5. If 2 moles of NO2 are placed in a 2-liter container and permitted to react at this temperature, what's the concentration of N2O4 at equilibrium? Okay, this is fairly straightforward. 2NO2 is in equilibrium with N2O4. They're both gases. The K for this is 7.5 at whatever temperature. So that's equal to N2O4 divided by NO2 squared. And initially, 7.5 molar. No, that's 7.5. That 2 moles in 2 liters. So 1 molar of NO2. All right, it's placed in that container, and the concentration of N2,4 at equilibrium is what? Okay. So we're going to get if we're trying to find out what N2O4 is, let's make it X. That means this value is X, and when we solve for that X, we'll have our value. That makes this one a half X. 1.0 minus 0, excuse me, my mistake. 0.5 X is this value, because it's a 2-to-1 ratio. This is 1. Oops, excuse me, went the wrong direction, didn't I? Minus 2X. There we go. Okay, so 1 minus 2X and X. So 7.5 equals this one on top. X. Is that what we're after? Yes. And on the bottom is this one. 1 minus 2X squared. All right. That's going to give us quadratic. And since this value is very large, we can't eliminate X. We can't estimate or assume anything about it. So we're going to have to expand this polynomial. That's 1, and this is 4X squared, and then minus 2X minus 2X is 4X. That's the bottom. Okay, bring that over here. That's 7.5 times 1, and then 4 times 7.5 is 30 minus 30, right? X plus 30X squared. Did I do that right? 7.5 times 4. Yeah. Okay, so that's on this side. That's equal to X. Okay, now we have to bring X over here and get our zeros on that side so we can use the quadratic equation. This would be a minus X, so this would be 7.5 minus 31X plus 30X squared equals 0. Place where you can mess up is when you use the quadratic equation, this is A. Right? That's the A term, this is the B term, and this is the C term. Okay. Is that the way I solved it in there?
I think so.
Okay. So what we need is X is equal to, I got it on the back of my calculator, minus B. So minus B is plus 31. Plus or minus square root. B squared. So minus 31 squared minus 4 times A, which is 30, times C, which is 7.5. Okay. And that's all over 2A, which is 30. Okay. Let's resolve what this is up here. Underneath that square root. 31 squared is 961. And then minus 120 times 7.5 is 900. Minus 900. minus. So that's 60, oh, square root, excuse me. I'll take square root of that. That's 61, square root of 61. 7.81, all over 60. Okay, two possibilities. 31 plus 7.81 divided by 60. 31 plus divided by 60. The first possibility is 0.647, or 31 minus 7.81 divided by 60 is 0.387. Two possibilities. All right, which one makes sense? Well, 0.647 times 2 is greater than 1.2, isn't it? So that can't be it. It won't work. It'd come out with a negative number. So it has to be 0.387. So X is 0.387 or 39. Okay? I don't like using the quadratic, but sometimes it's unavoidable. All right. Let's see. Scroll. Is that it? That's it.